In this video, we are going to learn about uncertainty principle and its applications. From the experiments for the determination of specific charge of an electron, it was shown that electron behaves as a particle. It was so because in the experiments, electrons get deflected by the application of electric and magnetic fields, which means that it has definite mass, momentum, and energy, which can be measured with desired frequency. Whereas from the diffraction experiments of electron done by Davison and Zermer and also G.P. Thomson, wave nature of electron was demonstrated. A wave extends through space and it is difficult to locate the exact position of an electron behaving as a wave at any given instant of time. This dual behavior of electron as a particle and as a wave presents difficulty in locating the exact position and momentum at the same time. This is stated by Heisenberg's uncertainty principle. In any measurement, there is always some uncertainty or error involved, though it can be decreased by using more precise instruments or modern techniques. According to quantum mechanics, there is a limit to the accuracy of certain measurements. This limit is not due to the measuring device or technique used, but is something inherent in nature. It is a consequence of the dual nature of waves and particles. Werner Heisenberg critically analyzed this uncertainty in measurements and formulated the uncertainty principle in 1927. It states that it is impossible to measure the position and momentum of a particle simultaneously and precisely. That is, if delta x and delta p are the uncertainties or errors in measuring the position and momentum of a particle respectively, then according to uncertainty principle, delta x into delta p greater than or equal to h bar by 2 pi. As the product of uncertainties is a universal constant, the more precisely we determine one variable, the less accurate is our determination of the other variable. The consequences of uncertainty principle is that we can only talk of the probability of getting a particular value for a variable. This limit of accuracy in measurement is because of the wave-particle duality. The product of uncertainties in coordinate and momentum is independent of the particle mass, wavelength of light used, etc. Hence, it is a fundamental law of nature. Other useful forms of uncertainty principle are 1. Relating energy and time, delta E into delta T greater than or equal to h bar by 2 pi, where delta E and delta T are the uncertainties or errors in determining energy and time, and the other relating angular displacement and angular momentum, delta theta into delta j greater than or equal to h bar by 2 pi, where delta theta and delta j are the uncertainties or errors in determining angular displacement and angular momentum. Generally, uncertainty principle can be stated as: it is impossible to determine accurately and simultaneously the values of both the members of a pair of physical variables which describe the motion of an atomic system. Such pairs of variables are called canonically conjugate variables. We now know three pairs of canonically conjugate variables, namely position and momentum, angular displacement and angular momentum, energy and time. So, for exam, if you are asked, state and explain uncertainty principle, first you write the statement, either the statement involving position and time or the general statement involving canonically conjugate variables. Also, while writing the statement, please remember to write those two words simultaneously and precisely. Then you write any one of the mathematical statement, either delta x into delta p greater than or equal to h bar by 2 pi, or delta into delta t, or delta theta into delta j. Then give one sentence as explanation. That is, any attempt to increase the accuracy of one variable will lead to a decrease in the accuracy of the other variable. Now, applications of uncertainty principle. Two applications are given in the syllabus. First one, absence of electrons inside the nucleus. That is, using uncertainty principle, you have to prove that an electron can never be a constituent of the nucleus. Second one is natural line broadening or uncertainty in the frequency of light emitted by an atom. Using uncertainty principle, we are going to prove that an electron can never be a constituent of the nucleus. The nuclear radius is of the order of Fermi. Here we start the proof by assuming that an electron is residing inside a nucleus of radius 5 Fermi. Since the maximum uncertainty in position delta x cannot exceed this value, we take delta x as also of the order of 5 Fermi. Now the uncertainty in momentum delta p is given as delta p greater than or equal to h by 4 pi into delta x from uncertainty principle. On simplifying, you will get delta P as greater than or equal to 1.054 10 to the power of minus 20 kilogram meter per second. If delta P, the uncertainty in momentum, is of the order of 10 to the power of minus 20, then momentum P itself must also be of the order of 10 to the power of minus 20. The energy corresponding to this momentum is quite large, and so we neglect the rest mass energy m0 c square in the equation of relativistic kinetic energy of electron given as T is equal to root of m0 square c raised to 4 plus p square c square. So kinetic energy becomes T is equal to Pc. On simplifying, you will get the kinetic energy of an electron residing inside a nucleus as approximately 20 mega electron volt. That is, for an electron to be a constituent of the nucleus, it should have an energy of this order. But experiments show that the energy of electron associated even with unstable atoms, that is electrons emitted during beta decay, have only a few mega electron volt, which is much less than the above energy. Therefore, we conclude that an electron can never be an entity of the nucleus. Second application is natural line broadening or uncertainty in the frequency of light emitted by an unstable atom. The uncertainty relation can be stated for the frequency and energy of radiation emitted by an atom. Let delta E be the uncertainty in energy and delta T be the average time gap between the excitation of an atom and the consequent photon emission. Then uncertainty relation gives delta E into delta T greater than or equal to h bar by 2. We have energy E is equal to h nu or delta E is equal to h into delta nu. On substituting in uncertainty principle, delta E into delta T greater than or equal to h bar by 2, we have delta nu is equal to 1 by 4 pi into delta T, where delta nu is the uncertainty in the determination of frequency of radiation emitted by an unstable atom. Thus, we can see that the spectral line emitted is not at all sharp, but it has some finite width, or in other words, the line emitted will have some broadening in frequency called natural line broadening. So we conclude that no spectral line will be emitted at a single frequency.